Hi everyone, welcome to Grade Up. In our previous lecture, we have learned the 5 property of a group. First one is the algebraic structure, second one is the semi-group, third one is the monoid, and the fourth is group, and the fifth one is the abelian group. So these are not the properties, but yes, first three are like the properties. And now in this lecture, we will be learning about the subgroup and the cyclic groups, all these kind of things. So let's get started. Finite group. So what is a finite group? As the name suggests, if a group having number of element finite, then it is called a finite group. So it is a finite group. What is the order of a finite group? Order of the finite group is the number of element in a group. Number of element in a finite group. Okay. And why it is not defined for the infinity group? Because you cannot count the number in a infinity group. Okay. So see, this is a group. This is a group, okay, where the set is having only one element, that is 0, and this is the binary operation, that is the plus addition operation. So this is the only finite group of real number with respect to addition. So this is a statement. Can you do any, you feel that it is a correct? Because if suppose okay, I added 0 plus 0 is equal to 0, 0 plus 3 times 0 is again 0. So always we do the addition, then we will be getting 0, okay. And they are saying that this is the only finite group with respect to the addition. If I added one number in that set, suppose 1, then when I am added 1 plus 1, then it become 2. So it is not following the algebraic structure property. So that is why I cannot add 1. If I added any element other than 1, then this is kind of other than 0, then this kind of thing will happen. If I am adding minus 1, again, then also it is not becoming group, because minus 1 plus minus 1, it's become minus 2, and that will not be present in this set. So it is not following the algebraic structure property. That is why this is the only finite group with respect to addition. See, this is also a group, okay. So how can I say that this is a group? It is following algebraic structure, semi-group, monoid, and the group. The group means you have an inverse for every element. You have an inverse for every element. Don't forget these properties, because these properties are the basis. Because you must remember them and try to practice them, okay. The cube root of unity is an abelian group with respect to multiplication, okay. So it is a finite group, and they are saying that it is an abelian group with respect to multiplication. So how can we say that it is an abelian group? So we will be checking all the properties. For example, like that, for algebraic structure we will be doing this omega 1, omega, and omega square. So it will be this, because it is multiplication operation, okay. And this will be 1 into omega into 1, omega, omega into omega, omega square, omega into omega square, omega cube. And you remember omega, what is omega cube? It is equal to 1. When, okay, it is equal to 1. We have learned this thing from in our 12th, okay. So it is 1, and omega square here, this is again 1, because it become omega cube. And what it will become? Omega 4, omega power 4. Then I can write it as omega 3 into omega, and omega 3 is equal to 1 into omega. It will become omega, okay. So you see that here, every element is this from set S. So yes, it is following the algebraic structure property, okay. And we know that multiplication is associative in nature, so it is following the semi group. And what about the monoid? Can we have an element? Here is an element that has act as an identity element. Yes, 1 is that element, okay. Now can we have the inverse for every element? Let's see. For 1, I will try for inverse. What is the condition? Is that you pick any element A, then B will be called as inverse if we get an identity element, which is here 1, okay. So what is B? B is equal to 1, B, okay, we need to get it. So for example, for omega, what is that element B? Can you tell me for this set, for omega, what will be that element B? I am saying it is omega square, because it will become omega cube, and omega cube is equal to 1. So the inverse of omega is omega square, and what is the inverse of omega square is omega. And what is the inverse of 1? 1 inverse is 1 itself, okay. Now more example on finite group. See this, these are the group and you need to remember them because they come again and again. Okay, so understand them. So it is starting from 0, okay, and go till m minus 1. So how many elements? M elements. How many? M elements, and it is addition modulo m. Okay, so when we divide something by m, how many possible remainder are there? There are m remainder starting from 0 to m minus 1. So when you pick any two element from this set and do the addition and then do the modulo m, then you will get from 0 to m minus 1. From 0 to m minus 1, because that is the possible remainder we can get. That is why it is following the algebraic structure property. What property? Algebraic structure. Now what is the second? Semi group. Obviously addition is a associative in nature, so that is why it is semi group. And what monoid? Yes, we having an element that can act as an identity element, that is 0. And now the another one is inverse. So for every element here there will be an inverse. You should try yourself. Okay, try it for example 2. What will be its inverse? So we need to add something. If I added m minus 2, then it will become what? It will become what? M, and m modulus m, it will become 0, which is the identity element. That is what we need to. So for 2, this is the element that will act as an inverse. That will act as an inverse. Okay, so this is an group. Obviously it is also commutative, so it is an abelian group. Okay, now see this. This is also very important. G is equal to Sn in multiplication modulo m. Okay, where Sn is defined as set of positive integers such which are less than n and relatively prime to n. So set of positive integer which are less than n and are relatively prime to n, that is what is Sn. Okay, and Sn with the operation multiplication modulo m is a group. Okay, for example S8, I am trying to verify whether it is true or not. You should also try with other examples. You can take it S16, S15, whatever you desire. Okay, so here it is S8 is equal to 1 2 3 4. Okay, this is also n. Okay, this is also n, because we doesn't define m. What is m? So we need to check whether it is a group or not. So what we do, we will, okay, n 1 3 5 7. Okay, 1 3 5 7. Okay, do it 1 3 5 7. Okay, and 3 5 7. Now 3 into 3 9, and when you take the modulus 8, what will we get? 1. Okay, or 3 into 5 15. When you take it modulus 8, what will we get? 7. Okay, 3 into 27 modulus 8 5. Okay, very good. 5 into 3 15. 15 modulus 8 again 7. Okay, 25 modulus 8 1. Okay, 5 into 7 35. 35 modulus 8 35. Okay, we get 3. Okay, and 7 into 3 21. Modulus 8 5, we get 7 into 5 35. 35 modulus multiplication modulus 8, then we will be getting 35, and that will be 3. Okay, 7 into 7 49, we will get 1. So see, every element here is what this set has. So it is following algebraic structure, and multiplication modulo m is gonna be an associative. Okay, here 1 is present. Which is present? 1 is present. That is mean it is an identity. We got the identity element, and whether we having inverse for every element, we need to check it. So we can check it from this diagram also. How when we do 3 into 3, what we get? An identity element 1. So it means that 3 modulo multiplication modulo m 3 into 1, we got that. So it means that this will be the inverse of that number. 3 itself is the inverse. Okay, and when we come to 5, then Oh, so here every element its own inverse, because 5 into 5 25, modulus 8 we get 1, and 7 also, 7 into 7 49, modulus multiplication modulo m 8, then we get 49, so it will be like this. So here 5 is the inverse of itself, 7 is the inverse of itself, and 3 will be the inverse of itself. Okay. Now subgroup and order of an element. Subgroup. So when you take the subset from a group G, then it is called a group. It is called a subgroup. Okay, that it has simple definition, but it should be a group. You take a subset of G, and if that subset is a group, then it will be a subgroup of G. This is the example, this is G and this is a subset of it, and the operation will remain the same. Okay, operation will remain the same. You need to tell whether it is a subgroup or not. For that, what we actually need to do, we just need to verify it is a group or not. It is a group or not. When you try for it, it is a group. We have also seen this example in our previous lecture, so try it. Okay. Now what is order of an element of a group? Order of an element of a group. Okay, so this is a group and A belong to that group. Okay, then order of element A is the smallest positive integer n, such that an is the identity element. So it means that suppose A belong to me G, and A1 will be obviously A, A2 is actually mean A, and the operation that we are having, that binary operation we are having, then we do it this and we get another number. Okay, and we will do till when n times where we get this, we will do this so and A, and we get the identity element. What element? Identity element E. So when we get that identity element, we can say that order of that A is n. We will try to better understand it with an example. See this, we have already seen that it is a group. We have already seen it is a group, and we try to find it. Now we need to find the order of each element. So first tell me what is the identity element in that group. Which one is the identity element? It is omega 1 or omega square, and the operation is multiplication. So obviously 1 is the identity element. Okay, and now we will need to get order of every element. So I am trying for what is the order of 1. 1 power 1 is equal to 1. I get the identity element, so I can say what is the order of 1. And now for omega 1 is equal to me omega. I didn't get one identity element. Omega square, that means omega into me omega, this will be omega square, and it is also not equal to me 1. Omega cube, that is equal to omega into me omega, and this will be omega square into me omega. We will get omega cube, which is equal to me 1. So the order of omega will be 3. What is the order of omega? 3. What is the order of omega? 3. Okay, so it is 1 and it is 3, and now we will try to find what is the order of omega square. So for that, omega square is equal to me omega square. Omega square is equal to me omega square, that will be omega 4, and that is equal to me omega. How it is? Omega cube is equal to 1, then it will become omega, so it is not also, and then omega square into me cube, so it will be omega into me omega 3 times, not omega. Omega square is equal to omega, and omega into me omega square is equal to me omega cube, that is equal to me 1. So what is the order of omega square? It is also 3. It is also 3. Okay, so we get it. What is the order of this of an element? You got it? Try it with for other group. Finding the order of an element, that is important. Okay, order of an element and in its inverse is same. So I told you that omega and omega square are the inverse. How they are the inverse? Because when you do the multiplication, you will get 1, which is the identity element. So they are inverse of each other, and order of an element in its inverse is same, which is 3 3. Both in case here 3 3. So we verified this statement also. Okay, order of an element is the divisor of order of the group in a finite group. Okay, so this statement means that for order of an element is always be the divisor of the group. Okay, so here what is the order of the group? That is 3. Order of the group here is order of G is equal to 3, and what is, and that order and order of element will always be the divisor of that 3. So how many divisor of 3 is 1 and 3, and you can see that order of an element are 1 and 3. So that statement is also verified. It is not proved, because proving something is different and taking an example is not a proof. Okay, we just verify whether it is true or not, but proving is something different and we need to do the formal proof. So it is not the proof. Lagrange's theorem. Okay, so Lagrange's theorem. If H is a subgroup of finite group G, then order of H is the divisor of order of G. It means that there is a group H and you take the subset and you get the H, and that H is a subgroup. But and Lagrange's theorem say that the order of H should be the divisor of order of G. Order of H is the divisor of order of G. But the converse of this theorem is not true. That means that if you take the subset that is the divisor of group G, that does not mean it is a group. It is a group. Why? It may violate algebraic structure property. If it is a group, then its order must be divisor of order of G. That is what is meant by Lagrange's theorem. Okay. So converse is not true. Try to understand the statement. Converse will not be true, because you may get the divisor of order of G, but for it to be a group, it must satisfy all these 5 properties. You need to verify it. Now suppose this is an example where we are given G and we are asked to find subgroup of G. Which of the following are subgroup of G? So how can I use Lagrange's theorem to do it? Okay, so what is the order of G? I am writing here order of G 0, 1, 2, 3, 4, 5. Here are 6 elements. How many elements? 6 elements. So order of G is 6. Now what is the order of H1? H1 order is 2. So 2 is the divisor of 6. So it may be a group. It may be a group. And see here, what is the order of H2? H2 order is 4. H4 is not the divisor of 6. 4 is not the divisor of 6. So I can properly say that it cannot be a subgroup. Using Lagrange's theorem, I can say that. To say that, we still need to verify. That is what the meaning of converse. I got the order, but I still cannot say that it will be a subgroup, because for that we need to verify it, and I am verifying here. 1, 3, and the operation is okay. 1, 3, 1, 1, 1, 1 and 3, 4. Okay, this is also not a group. Not a group. You see, its order is the divisor of order of G, but still it is not a group. Okay, I am doing here for this 0, 3, 0, 3. So it will be 0, and this will be 3, and this will be again 3, and this will be 0, because it is modulo 6. It will become 6 and you have to take it. So yes, it is a group. Okay, algebraic structure property is verified. Other properties also verified, because the operation remain the same, and 0 will be the identity element, so it will become the monoid. Yes, it is a group. Okay, inverse, when you need to find the inverse, so 0 inverse is 0 and 3 inverse is 3. 3 inverse is 3, because this 0 is the identity element. I got it. So yes, it is a group. But using Lagrange's theorem, we can simply, by seeing order, we can say it is not a group. Now cyclic group. So what is cyclic group? A group G, star is called a cyclic group. Okay, if there exists an element A belong to G, such that every element of G can be written an for some integer n. This statement is important. Every element of G can be written an for some integer n, then A is called generator or generating element. So we need to find these are the 3 examples. We need to say whether they are cyclic group or not. How can we do it? By finding the generator or generating element. And what are generator and generating element? They can generate all the element of the group. Okay. So I will say in this I am saying that 1, I am thinking that 1 will be the generator. So 1 power 1 is equal to 1, okay. 1 power 2 again 1, 1 power 3 again 1, 1 power 4 again 1. There is no way I can get minus 1. There is no way I can get minus 1. So 1 cannot be the generator. Okay, 1 cannot be the generator. What about minus 1? There are chances. 1 minus 1 is equal to me minus 1. Minus 1 power 2 is equal to me minus 1. What is the operation? Multiplication. Minus 1 into minus 1, 1. So yes, I can generate 1. I can generate minus 1 as well as minus 1 from this. That means it is a generation. And what is its order? We get the identity element in how much power? 2. So its order is 2, and that order is same is equal to order of group. Okay, see this point. Okay, that order is same is equal to the order of group. Now this example. So here what we need to find? Generators. Okay, so for generator 1 cannot be the generator because it is multiplication, as I have proved here. Omega is maybe the generator. Let's see. Omega 1 is equal to omega. Omega 2 is equal to means omega into me omega, that is multiplication omega square, and that is equal to me omega square. Okay, this is also an element of G. Omega cube, this means omega into me omega. This will become omega square into me omega, and it will become omega cube, and it will become 1. So 1, 2 and 3, all 3 elements are generated by omega. All 3 elements are generated by omega. So omega is a generator. Okay, here minus 1 is the generator, here omega is the generator, also omega square is a generator. You can try it, I am not doing it here. Omega square is also a generator. And for this one, what is the generator? Think. What is the generator here? 0 can be 0 plus 1. 0 plus 1, 0 plus many times 0, it is always be 0. So 0 cannot be 1, 1 can be. Okay, so here 1 is the generator, and I think 3 is also the generator. I will try for 3, whether 3 is a generator or not. 3 power 1 is equal to me 3. Okay, 3 power 2, that is means 3 modulus 4, 3, that is equal to 6, and 6 we will get 2. Okay, 3 power 3 is equal to me 6, 9. Actually it will become 9, and when you do it you will get 1. Okay, 3 power 4 is equal to me 12. You will get 0. So yes, 3 is also a generator, and 1 is also the generator. Okay, so here we got 2 generator, here also 2 generator. All these are cyclic group. So question may be like that, you need to find the generator, also number of generator we will be seeing. Some properties of cyclic group. Let G comma star be a cyclic group of order n with generator A. Okay, simply go. A inverse is also a generator. If A is the generator, then A inverse is also a generator. The order of generator is equal to order of a group. That is what I am saying here. Seen there. The order of minus 1 is 2, and that is the order of group G. How? Because the number of element in G is 2. Okay. Here the number of element in G is 3. And what is the order of omega? 1, 2, 3. 3, because with 3 we get the identity element. That's why order here is 3. And here also the order is 4. So order of a group and order of a generator are same. That is the meaning of that statement. The number of generator in G is Sn, where n is the number of element in G. And what is Sn? I told you in few previous slide back, I told you what is Sn. So Sn is it is a positive integer less than n that are relatively prime to n. Positive integer less than n that are relatively prime to n. Okay, so remember that also. This is important. Okay, Am is also a generator of G if GCD of m comma n is equal to 1. So if A is a generator, then Am is also a generator when the GCD of m and n is 1, and n is the order of G. So you can verify this point also by taking an example. Try to do it, because the more you verify, the more confident you get with these kind of properties. So try it. Now see this GATE 2009 question, and this is saying that they are the cyclic group, and this is the thing what we we used to draw the table, and that is they got it. Okay, you can say that, you can see that it is following algebraic structure, and we need to find whether, okay, which of them is generator, either AB generator, BC, CD or DA. We need to find it. Okay, but before going that, it is saying that it is a cyclic group, so it should follow all those properties that we know that are defined for a group. So we want to verify it. I want to know what is the identity element here. When you do, what is identity element property? If suppose E is the identity element and you do operation, binary operation with any element X, then you will get X. Okay, so if you say here A got A B again B, A C C, A D D, so this is my identity element. It is not happening with other also, because we don't get A here, B here. Okay, so A is my identity element. That is good. Now identity element, okay, this is the multiplication operation or whatever they are saying. I am okay, associative, it is become the associative. Now we need to find, if I ask you what will be the inverse of C, can you tell me from this table what will be the inverse of C? What will be the inverse of C? To say that, what you need, suppose C, that operation, whatever it is, I don't know it is multiplication or what it is, and this is C inverse. What should I get? Identity element, and identity element I prove it A. Okay, and C, where I got identity element? Here. And what is that element? D. So C inverse is D. That simple it is, very simple. Okay, but the question is asking which of them is generator. So generator means that you need to generate all the element. If I try with A, okay, I am trying with A, A1 is equal to A, A2 is equal to A star A, and that is again A. So it cannot going to drive it, because it is always going to drive A again. Okay, so it is not. And B, for B, okay, B, we got B1 is equal to B, B2 is equal to B cross B, and B cross B is A, B cross B, A. So we got A, we have derived B and A. Now I want it, and A is the identity element, so order of B will become 2. Order of B will become 2. Remember that order of an element, I told you earlier. And here our how many elements are there? 4 elements. So order of this group will be 4, and order of B is 2. So it cannot be a generator, because this property, order of generator is equal to order of G. So this is not gonna be a generator, and I am not checking more here for B. Now C, C power 1 is equal to C, C square is equal to C cross C, and what is C cross C is B. Okay, I got B here. C3 is equal to me, that is C square into me C, and that is B. This is not into, this is some operation, binary operation, B into C, B, C, we got D. Okay, I have generated 3 elements, C, B and D. What is left? A. Let's try C4, that it will be C cube into me C, and C cube is D, D into me C, so D, C, we got A. So yes, C is the generator, C is the generator, C is the generator, definitely C is the generator. Okay, but here it is not given, maybe other, D may be also a generator. How can I verify that D is generator? By doing it, it may take some time, but it is easy to do. Or also I can use the property, that is, if C, A is generator, then A inverse is also a generator. I want to try to find the inverse of C, and I told you what is inverse of C? D is the inverse of C. What is the inverse of C? D is the inverse of C. So obviously D is also generator, because of that property. D is also generator. So which one is the right option? C. C is the right option. C and D are generator. So this type of question can be framed from cyclic group, subgroup, finite group and group theory. There are many good questions. You need to practice, because practice is the key in mathematics. Do lot of practice and don't miss any question from mathematics. Discrete mathematics is all about reasoning, so don't miss it. Try to properly understand it and then do some practice, and you will gain confidence and you will solve all questions. Okay, thank you.